All right. So you might have been hearing about a lot of different things. So this semester, so I plan to, or I will be talking about collaborative autonomy and AI. So I prefer if it is more of a discussion. If you prefer, feel free to stop me and ask any questions that you may have. How many of you are sure what collaborative autonomy is? Sort of. Okay. All right. So before we get into the talk, I'll just quickly talk about what I do, my interests, and so on. So I'm Vignesh Narayanan. So I'm an assistant professor here at the AI Institute and Department of Computer Science. So my research area is broadly three, and they are dynamical systems and control. So this is a field which is mainly associated with applied mathematics. So you study systems that evolve with time. You try to understand, model these systems, and try to control or steer these systems in a desired manner. So that is dynamical systems and control. The second one is AI. So AI is very broad. There is no specific definition that I would attach to it. But the work that we do in our group is mainly constrained with designing computational methods or learning methods, building neural network architectures with theoretical guarantees, and using them in the context of reinforcement learning problems or data analytics. All right. And the last area is related to neuroscience, particularly computational neuroscience. Here, our goal is to use tools from dynamical systems theory, tools from AI to study neural systems and try to understand the behavior of neural systems, neural circuits, their organization, try to use data that is usually measured or availed through devices that we have access to, like EEG, fMRI, to study such systems. All right. So, what are the type of applications that we are interested in? Broadly, the first set of applications target cyber physical systems. So, these are systems that have a physical system component, uh, and there is a cyber component, which includes communication networks, communication channels, and these could be wired, wireless, uh, any type of communication that facilitates coordination between a bunch of physical systems. Some examples are given in this slide. These are quite broad, common, and they are typically infrastructure systems or critical systems that are very important to understand and control. So some of the problems that we are interested in this application domain has to do with control synthesis. So an example could be, what is the best way to transfer power from a generating station to multiple loads? How to distribute them effectively? What sort of strategy should be used to distribute water in a water distribution network to prevent losses? How can we signal or design signals in transportation network to facilitate traffic flow smoothly in critical times? So these are sort of control synthesis problems, and they are usually targeted towards improving the operational efficiency of these types of systems. The second set of applications are also set of dynamical systems, but these are systems that usually are naturally occurring systems. They are not engineered by humans. So some of the problems that are important and that are associated with these classes of systems is we don't actually understand some of the interdependencies in the system. So we want to use the data that we measure from these systems, try to model them, try to understand or gain insights about the working of these types of systems, right? So again, there are some of these examples are something that everyone is familiar with, epidemic networks, social networks, drug delivery system, and neural networks. Uh, and the last target application is population systems. So these are systems that are large populations of dynamic units. So it is typically it has to do with swarm robotics or quantum systems or opinion networks. These are systems that have multiple elements, and each of them, they have their own agency. It means they evolve on their own with respect to time, and they evolve through interactions with other units in this network and so on. And the task that we are interested in is trying to understand these systems again from data, how to model these systems, how to understand their properties. For example, if you are interested in opinion dynamics, a natural question is, after this talk, will I be able to shape your opinion about a particular topic? Say, for example, collaborative autonomy, which is the topic of this presentation, right? So being able to answer such question is typically referred to as controllability analysis of such systems. So this is a type of problem that is very fundamental in nature, and we are interested in problems like that. All right. The last thing that is something that is connecting each of them is that most of these problems, they have some form of dynamics. So systems are having some dynamic evolution, some parameters or some variables of these systems evolve with time. Most of these systems are connected with other systems, and they all generate lots and lots of data. So one of the key goal that uh, we have in our group is to use data from these types of dynamical systems, try to make sense of this data so that we can uh, design systems that can monitor themselves, communicate with each other, and self-govern, right? So that is the overall goal of our group. All right. Now, for this talk, I'm going to focus specifically on collaborative autonomy. So we'll try to understand what is collaborative autonomy, what are some of the design problems associated with it, why do we need AI, because the title of this presentation is AI for collaborative autonomy. So why do we need AI for collaborative autonomy? And we'll look at some types of design problems that we are currently looking at. And if time permits, we'll look at an example. All right. So what is collaborative autonomy? So collaborative autonomy has to do with systems where there are multiple autonomous agents. Each of them, they work together towards a common goal while maintaining their individual decision-making capabilities. So there are three components there that are very important. The first component is there should be at least two or more agents. The second component is each of these agents have their own agency. So uh, when I say agency, what I mean is they can take decisions on their own. They have that capability. The last component is that these agents, which can take decisions on their own, exist on their own, they come together, work towards a common goal, right? So these three components constitute systems that are collaboratively autonomous systems. Okay. Some of the design problems associated with this setting is that if you have multiple agents, you have to assign role, you have to assign tasks for each agent. You should be able to have communication among these agents. Then you should have some way to inform other agents about the things that each of them have learned. There should be, each of these agents are autonomous, so they can take local decisions, but these local decisions should be designed such that they uh, help towards achieving the global objectives. And if there are conflicts between these local decisions, there should be a conflict resolution mechanism. There should be trust among agents, in the sense that if there are multiple agents that are helping to accomplish a particular task, each agent should, while doing their job, trust that other agents will also do their job, right? So that is very important. If there is some agent that is not working due to some reason, there should be adaptability. Other agents should take over. There should be safety and scalability of these types of systems, right? So all of these are important design problems, and each of them is a research problem in its own right, with a lot of challenges, a lot of decisions that as a designer you have to make in solving these problems, all right? The next thing that I have is what is known as ill-posedness. So many of these problems are, in mathematical terms, ill-posed problems. So if you have problems that, for example, the easiest example that I could give is everyone is familiar with this matrix problem, AX equal to B, right? Solving for X, right? So if you all recall your high school math, there are conditions that dictate when solutions exist for this problem. Anyone remember the conditions? So there are different conditions. So if you want this solution to be a unique solution, you want A to be a matrix that can be inverted. You should have A to be a non-singular matrix, so you can take inverse of the matrix. If you want to have solutions, but not necessarily unique solution, you can have a singular matrix, but you should have pseudo inverse for A. And you can have the case where there is no solution is when the number of unknown is greater than the number of linear equations that you have access to. So the matrix itself is skewed. Uh, it's a short matrix or wide matrix, right? So there are different conditions under which solutions exist even for these small problems, right? So a well-posed problem is one where you know that solution exists, right? In theory, there should be a solution. If you know that in advance, then you can have a systematic approach to find that solution. In many cases, the problems are ill-posed, like the case where the matrix is too wide and short, right? So there is an inconsistent system of linear equations. So you don't know if you have any solution or not. So these are called ill-posed problems. And wherever you see mathematically ill-posed problems, that is where there is a strong motivation to use learning strategies, right? So if you don't know that there is a systematic approach to solve a problem, you can try to formulate a learning approach or a learning formalism under which you can search for a solution, right? Does that make sense to everyone? All right. Now, given that we have defined what a collaborative autonomous system is, what are some of the problems associated with and why we need AI, I'm going to talk about four different setting where we are currently actively working on different problems, right? So in the first setting, you have a design problem where, uh, as a designer, we have the freedom to design individual agents and their collaborative mechanism, right? So we define a goal and we design individual agents and we design how they can collaborate. This framework, the end-to-end framework, is totally designed by the user. The second type of problem is your goal is to only design the collaborative mechanism and only a set of autonomous agents. There are other agents which are autonomous and they have their own behavior. And as a designer, you cannot change that behavior or modify this behavior explicitly, right? So you can design only the collaborative mechanism and a subset of agents. Third and fourth setting are a little bit more challenging in the sense that you only design a set of autonomous agents with an objective to coordinate with other set of autonomous agents. So here the collaborative mechanism is also not fully under the designer's control, and there are other agents which behave in a way that is autonomous for those agents, and we don't have a way to steer these agents. But this is in the third case, it is a I specifically label it as a cooperative setting because in the third case, the other agents which we don't design, they are autonomous, but their goal is aligned with the goal for which we are designing other set of agents. Does that make sense? So there are a bunch of agents. We cannot design a subset of them. They are autonomous. They take decisions by themselves, but their goal is aligned with the goal that we have. So we can design the other set of agents so that the cooperation can happen by through this subset of agents. And the last case is a setting where we have to design a subset of agents and there are a subset of autonomous agents and their goal need not align with the goal that we have, and we may have to try to enforce or try to steer goal oriented behavior through the subset of agents that we design, right? Does that make sense? So we'll see what these are in specific examples, but these are the four type of design problems that we are currently looking at. The first one is fairly easy to grasp. Here we do the end-to-end design and the application domain is autonomous robots, right? So you have a bunch of ground robots, you have a bunch of drones, bunch of surface or underwater robots. These are all heterogeneous robots. You can design individual robots. You can design them such that they have their own independent decision-making capability. You can also assign goal for each of them such that you have an overall task that you accomplish, right? So this is the case where you have full control as a user or as a designer, right? So you choose how each agents behave, you choose how they cooperate and collaborate, you design what the collaborative or conflict resolution mechanisms are, right? So some of the problems that we look at are for redundancies. So if agents in this case lose communication, or if there is uncertainty in communication, how to handle that. So some of the application areas, for example, if you have a bunch of robots that are trying to do reconnaissance or trying to uh, figure out if there are people that are in remote areas during crisis, things like that, you don't want to lose privacy. So another problem in this setting is data privacy. So you want to have good communication policy, as well as the communication should ensure privacy preserving behavior. And then the last component is if there are certain agents in these type of robotic systems that stopped working, either because they lost fuel or because they crashed onto something in the environment, then there should be uh, a capability to detect compromised agents and try to uh, reorganize the rest of the team to still accomplish that task, right? So this is the type of the design problem, which is end to end. You have complete control as a designer to specify each component of this collaborative mechanism. All right, the second set of problem is human in the loop systems. So you can take the same example. You have a bunch of ground robots, you have a bunch of drones, you can have underwater or surface robots. Each of them, they can have their own controller so that they can do their own task, but you can introduce a human operator or a human supervisor monitoring these systems, right? So there are some cases, for example, where the goal can change, and this goal is not known before the start of a task, right? So for example, if you are trying to figure out oil spills on the surface of oceans or water bodies, or if you are trying to find the boundary of a fire, then the agents are exploring. They don't know specific, they don't have a specific goal. They just try to explore. But the human supervisor, if the supervisor gets additional information, the supervisor can introduce control to these agents to steer these agents appropriately, right? So there is, compared to the previous case here, in addition to a lot of these robotic agents, you introduce another component, which is the human component, right? So there is a uncertainty. So some of these uncertainty comes from the human operator or the human supervisor. So I make this differentiation between supervisor and operator because there are cases where there is a supervisory nature of intervention by humans. That is the example that I gave, where the human supervisor simply monitors what all the other agents are doing. If there is a robot that is going in a direction that is not going to be useful for a specific task, the human supervisor can reorient that agent, right? The other term that I use is human operator, and that is the situation where you have an explicit control. So, for example, you have remote operation of robots, you have remote operations of drones, right? So, these are situations where you have uncertainty coming from environment. For example, if you have a very clouded or foggy weather and you are trying to operate a drone, it's better that you let the controller or the sensors in the drone monitor and correct its path rather than a human operator correcting its path because of poor visibility, right? On the other hand, if the terrain is bad or if it is highly windy with clear visibility, you do want a human operator to be a stopgap to prevent the drone from crashing on things, right? So there are situations where you have a human operator who is part of this collaborative team of robots, right? So this is the case where you cannot design the behavior of the human operator, right? So They have their own autonomous decision-making capability, but you can design other robots, their behavior, so that you can design mechanisms to detect the human operator's input, to decide whether to follow the human operator's input or to take over from the human operator's input, right? So this is the type of problems that are relevant in this second case, where you have a human operator or a human supervisor. You want to learn to understand the intention of this operator or the supervisor and try to adapt to these inputs that are coming from the human, right? So here you don't have the full end-to-end design uh, choice, but you have some form of uh, design priority, in the sense that you can design a lot of things, and you can design an adaptive mechanism of how to incorporate the uncertainty which is coming from the human uh, in the loop. All right. Any questions so far? Is all right. All right, so let's look at the third case. The third case is the case where you are designing a subset of agents and you have a cooperative setting, right? So this example is a classic example of designing chatbots or health assistants or simply a virtual assistant, right? So you have some AI system that answers queries of users, right? Uh, do you see why this is a collaboratively autonomous system? Yes? No?
Agents that we're designing, trying to get to with a filter of like whatever functionality they align its goals with the
Mhm. Right. So let's take it one step at a time, right? So a collaboratively autonomous system should have two or more agents, right? In the simplest setting, you have two agents when there is a chatbot or a virtual assistant involved. The first agent is the user, human user. The second agent is the AI model, that is to which the user is providing some input, asking some queries, and so on, right? So that is one. The second component, each agent have their own decision-making capability, right? So the human user can choose to ask whatever the user wants, choose to respond in whatever way the user wants. Similarly, the chatbot has its own control mechanism, right? It has its own AI uh, policy that determines how to respond to any query, right? So they have their own agency, right? Third, what is their shared goal? Their shared goal usually is to get clarity or get something, some information that the user want. The AI chatbot also intends, its goal is also to provide information in such a way that the user is satisfied with the response of the AI bot, right? So you have all these three components. You have two or more agents, they have their own autonomous behavior, and they have a common goal, right? This is a setup which is also a collaboratively autonomous system. But here you have less control as a designer, because you have you can only design this AI model that generates some form of information to a query, and how the user behave is totally uh, open, right? So you don't have uh, a lot of you cannot design for all possible response from a user. That, is, is that making sense? Because each user can respond or ask question in a way that is uh, that cannot be codified in some formal way, right? And you can design some form of collaborative mechanism in the sense that if the question is not clear, you can try to prompt this AI. You as an AI model can prompt the user to get clarity on the questions that was asked to it by the human user, and it can enforce some form of mechanism to ensure safety, trust, and reliability of these collaboration. Does that make sense? So this is the type of problem that is also something that we are looking into. Specifically, we are interested in ensuring safety and trust between this collaborative systems, right? The last one is this problem, or this project is called Information Competition Simulator. So the goal of this problem is to understand how opinions evolve in social networks, in general opinion networks, right? So here, again, this is a collaboratively autonomous design problem, system design problem, because you have multiple agents. Each of these agents represent a user in the social network. Each of them, they can take their own actions, they have their own agency, and not all these agents have a common or at least an explicitly uniformly defined goal, right? Their behavior is not goal oriented, that is uniform across all of them, right? So you want to design some form of information dissemination mechanism that helps reduce or mitigate misinformation or disinformation in these type of social network setting, right? So again, this is a design problem. This is a important design problem in the context of collaborative autonomy, and it is more challenging because there is a lot of variables that as a designer you don't have control over. You can only design some dissemination mechanism to spread information that are helping to steer the behavior of the rest of the agents towards a common goal, right? So this is the type of setup in the collaborative autonomy class of problems, which is uh, very challenging. Obviously, another thing I should have mentioned, all of the problems so far that I have mentioned are all ill-posed problems. There is some data generated by each of these agents or each of these systems, but we don't know everything about other agents and other systems in these settings. So we have to incorporate some form of learning, right? So in this particular project, our goal is uh, multiple folds. So let me elaborate a little bit. So few years back, at least if my memory serves right, at least 4 years back, you could get access to Facebook posts, or you can download freely the X posts. You can get an API access to some of the posts, user posts, right? And you can use this information to try and model or understand how opinions on particular topics have evolved over time, right? But now this information is becoming rare. We cannot get this information easily. At least we have to pay a lot of money to get that information, right? Second, it also is a concern that if you get this information, you are going to infringe on the privacy of the users. So you don't want to do that as well. Without this data, how can we understand this critical problem of how information is spreading in networks, how clusters of opinions are formed in opinion networks, how to understand misinformation, why certain type of information spreads faster than the others. These are problems for which we cannot have answers if we don't have good data-driven analysis framework because we don't have good resource in the form of rich data sets. The other form of analysis is called model-based analysis. There, you don't have a lot of data, but you have a hypothesis model that you develop, and you try to get these model as close to how the actual network works through the limited data that you have, right? And you try to understand through this model how opinions evolve in a network, how to identify or mitigate or reduce the spread of certain type of disinformation in the network and things like that, right? So this is this type of problem that is something that we are working on. And so any questions so far? So far I just mentioned what is collaborative autonomy, the type of problems that are relevant in this context, and the type of problems that we are working on, right? So I'll quickly talk about this work we presented in NeurIPS last December. So this is associated with the last class of problem that I talked about, where your goal is to use model-based methods to understand how information spreads, to design specific agents in the network so that you can mitigate spread of misinformation. Okay. All right. So the problem itself is called information or intervention planning. So intervention planning, so to understand what it is, so we'll try to understand the context, right? So the context is again a simplistic version of a opinion network or a social network. So it is modeled as a graph. You have a bunch of nodes or vertex. Each vertex models an agent. Agent's behavior is modeled by each vertex, and each vertex is connected by edges, or pairs of vertices are connected by edges that model the trust between the agents, right? And an information sent by an agent is received and processed by all the connected agents in the network, and how they process, to which agent they receive this information from, they are all modeled by a dynamic model, which is usually used in computational social sciences. Okay. So given that you have this network or a graph where each agents, they have their own way of sharing information or processing information, we consider a problem where there is a subset of nodes which is spreading disinformation on a particular topic periodically. So every time unit, we update the model. This particular node spreads a particular type of information about a particular topic, right? So in this context, intervention planning is a problem where you want to identify specific nodes in the network and try to spread or share the official information to that node, right? So here there are a lot of things that have to be defined. So what is an official information? So official information, so for example, uh, we took in this paper, we took the example of NeurIPS, information about the NeurIPS conference itself, right? The website of NeurIPS has all the information that you need about the conference. So that is the official information about the NeurIPS conference, right? So if some node in this example, if there is a node in this network which is spreading information, I think in so if you look at that box, we have, for example, a topic. The topic could be any statement, like the submission deadline for new RIPS is May 22nd, right? An opinion on that topic is the belief that the statement is true or false, right? So you can model belief on a particular topic using numerical values that uh, either indicates that the agent believes the statement to be true or false or anything in between, right? All right. So a misinformation or a disinformation could be a particular agent in the node that intentionally spreads NeurIPS submission deadline May 22 is a false statement, right? So this is a form of disinformation that is spread by a particular agent in the network. Now, intervention planning problem has to do with identifying the nodes in the network to which you have to share the information that this statement is true, right? Then the question is why do we do that? What is the goal? The goal is to reduce the spread of disinformation through the network, right? So you want to share the official information by selecting specific nodes and sharing the official information to those nodes in such a way that the spread of the wrong information is minimized. Does that make sense? Right. So this is the intervention planning problem. So yes, that is the planning part, right? That is the solution approach that we propose in this work, right? So, all right. So again, there are a lot of things that are variables that are very important, right? So if you are going to plan, do we know the opinion of all the agents in the network? We don't know. So if we don't know that, how do we identify specific nodes, right? What type of information is needed to solve this problem effectively? How do we incentivize correct information versus wrong information? These are problems that are very important. Another problem is, so if you think about social networks or any of the social media networks that we have seen, the number of users could be in millions, right? So for such a vast network, if I design a solution approach, can I scale that to millions of nodes in a realistic setting? Right? It's a scalability problem, right? All of these are important problems, okay? So there are lots of uh, variables as well that have to do with the individual agent's behavior, right? Not all agents in a realistic setting shares information all the time. Some of them are simply inactive. They don't share anything, right? So if we share the right information to those inactive agents, it's basically not helping reduce or mitigate misinformation spread by other agents, right? Do you see what I'm saying? So there are a lot of these problems, right? So to study this problem, we conducted or we started with some of the basic computational social science models. There are many of them, and we tried to generate a lot, uh, a variety of synthetic networks with hundreds and thousands of agents. Each of these agents' behavior were defined by these computational social science models. We took few models, 3 or 4 different models, a variety of network architectures or graph structures, and we simply studied what are 2 types of learning methodology. First is called ranking or supervised learning method, where we used ranking algorithm. The ranking algorithm, how many of you are familiar or heard about ranking algorithm? Yeah. So ranking algorithm is a very common algorithm. It's a very popular algorithm. So if you do a Google search, the results are populated through ranking algorithm, right? So you have a bunch of possible candidates, you organize or rank which of them are important, and you identify or present those results. So similarly, in this ranking algorithm, what we did was we tried to simulate different candidates, right? So we have to identify nodes through which we have to share the right information. So we simulated a lot of candidates, and we tried to share the right information through those candidates, and we recorded the eventual behavior of the overall network. The eventual behavior was quantified using infection rate. So the number of infected nodes versus the total number of nodes, right? So for all possible candidate nodes, we tried to record this information. And based on that, we tried to train a supervisory learning model, which after training, when we share a network node, it will tell whether that node should be chosen as the node through which you have to share the correct information. So this is posed as a classic node classification problem using a GNN. And we reported some results based on that. One of the obvious challenge with that is to do this ranking based strategy, you have to actually simulate a lot of variations, a lot of candidates, a lot of over a period of time to identify or to generate target data sets using which you can train a supervisory learning model, right? The second approach we did was using a reinforcement learning mechanism. So here we assume that the as a designer, I only know the agent or the node which is spreading the wrong information. I don't know about the opinions of other agents. I only know which agent or which node in the network is sharing the wrong information, right? Just with this information, we designed a graph convolution network with different rewards. Each of these rewards are categorized as knowing only the local information or global information about the network. And we try to uh, use this learning strategy to come up with a model that will simply identify at every time instant which node to identify and share the right information to, that will result in the minimization of the infection rate, or which will reduce the spread of misinformation, right? So that is the second approach we tried. So through this, we have at least, for example, uh, 24 different data sets we have generated and shared with the broader community that works on computational social science. There are several open source data sets that have been currently used. If you notice, these data sets, V here is the vertex in that graph, right? So you will see that the total data sets that are available currently, they have very small uh, sized graphs. And it is not easy to use these networks or the data sets because they don't also have information across time. They only have information about the network structure, right? So we had to generate a lot of data and share them. And then we answered some important questions that are useful. First, for example, if I train models just based on how quickly they can share or spread the correct information through the network, whether that is better than uh, designing models that try to explicitly minimize infection rate. So for example, you read this. So if we prioritize fast response, it may overlook total control, or it may not perform as well with respect to reducing the infection rate. In the short term, it may work well, but over long time periods, it doesn't work at all. The second type of question involves observability. So if we observability, as I said, is whether we will know information about all the agents, subset of agents. We don't know anything about the network at all. So we found that there are some cases where you don't have to know everything about the network and you can still do a good job in terms of reducing the spread of information in these types of synthetic networks. And then we also found that you can, our approach that we have proposed is scalable. So for example, I can simply train a graph neural network or graph convolution network using our proposed training algorithm that only sees data, synthetic data of networks that are having only 10 nodes with different topology, right? If I train my model with data from networks that are 10 node networks, uh, I can use the model to generate plans for networks of any size. It can be over 100,000 vertex edges, and it still works as well as if the network that we are testing it on is a 10 node network, right? So we showed that we can do scalable planning with the proposed algorithm that we have. All right. All right. So I'm going to just simply stop here. If you have any questions, I can answer. Otherwise, I assume you understood everything I said. All right.